Alright, so we've talked about a lot of different integrals, but let's go back to one that we should be able to recognize. The idea, so if I have x over the square root of 1 minus x squared dx, I can take u to be 1 minus x squared, and then I can use my substitution methods, and I get this, right? That should be something you feel comfortable with using u substitution. Now, if I did this without an x on top, one thing that hopefully you remember from the table of integrals is the idea that that's actually the arc sine of x plus c, or the inverse sine of x plus c. Now, we derived that when we talked before by taking the by looking at how inverse derivative, or the derivatives of inverse functions are related to the reciprocals and all that. So that may be a little hazy for you, but we were able to derive this from this. But there's ways to get there without having to sort of use clever differentiation tricks. And you're going to need that if you have something that looks like this, the square root of 1 minus x squared. So how do we solve that? You might say, okay, well, what do I take for u? Because no matter what I do, the du that I need, that sort of x on the outside, doesn't exist. And there's not a quick table that I can use for that. So I have to be clever. I have to be a little more clever. And the way we do this is actually by constructing a triangle. So notice we keep going back to classical geometric shapes. We're going back to a right triangle. And we're going to exploit the idea of the Pythagorean Theorem. See, what happens is I notice that I have some sort of a squared minus some sort of something squared minus something else squared. When you see stuff that looks like that, it's natural to think about Pythagorean identities, something squared minus something else squared. Because this is a squared plus b squared equals c squared, but if you subtracted one of these over, it would be like c squared minus b squared equals a squared. So we're going to exploit that. So what we can do is we can construct a triangle, just an arbitrary triangle, and I'm going to pick one of the sides to be this quantity, this 1 minus x squared quantity, which is kind of a weird thing to pick. But what we're going to do is we're going to make a triangle where a squared, or a, b, and c meet certain criteria. So if I wanted that to be there, and I wanted like there to be a 1 here, because 1s are easy to deal with. Well, I know that a squared plus something squared equals c squared. So I know that this thing squared plus something must equal 1. Well, if I square this, I end up with 1 minus x squared. And I know that I have to end up with 1, so the only thing left over is x. So similarly, we write it like this: 1 minus x squared, square root squared plus x squared equals 1, right? You could work that out and clearly see that that's how that is. But now that we have this triangle, what we can do is we can actually represent substitutions this way. I know this is really strange because you've probably thought to yourself, well, usually I just say u equals something or t equals something and I'm just done. And now I've got this triangle, but all we're trying to do is we're trying to set up a relationship. And as long as that relationship is consistent, it doesn't actually matter that it wasn't just a equals b. It says, okay, I'm going to relate it and constrain it by this triangle. So I'm going to say, okay, well, if this triangle holds, and this is an angle on that triangle, then sine of theta is x because it's opposite over hypotenuse. Okay. So if sine of theta is this, well then if I take the derivative, just like I do with a normal substitution, if I take the derivative, I get cosine of theta d theta equals dx. So instead of being, u equals blah, 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 I'm just saying something equals whatever that x is. Then I take the derivative, I get a dx. Okay, simple enough. Now what I also get, which is interesting, is that cosine of theta, which is adjacent over hypotenuse, cosine of theta is in fact exactly equal to this quantity, that 1 minus x squared, or square root of 1 minus x squared. So now that I have this, I can say, okay, well that square root function just becomes a cosine, and that dx also becomes a cosine of theta d theta. So I have a cosine of theta d theta, which then reduces to this, cosine squared theta d theta. And hopefully you felt comfortable with the last section, and you realize, oh, I can actually use half-angle identities here. like I said, that's theta plus 1/2. Well, actually, yeah, I skipped a step here. That would be 1/2 1 plus cosine of 2 theta, and then when I take an antiderivative, I get this piece. And then I used a little bit of another trigonometric identity we haven't discussed, which is sine of 2 theta is 2 times sine of theta times cosine of theta. So that takes care of the 1/2. So I have sine theta and cosine theta. So why would I want to do that? I want to stop right here, because I have a theta, and I have a sine theta, and I have a cosine theta. But that's problematic because there's nothing I have here that says theta equals something. So what do I do with that? Well, what I do is I use the properties of inverses. If I know that x is sine of theta, then I know that theta is the arc sine of x, right? That's how inverse functions work. So anywhere I saw theta, I can replace with arc sine of x. But over here, I don't actually have to replace theta. I can actually replace sine of theta or replace cosine of theta because they're already defined up here. I said, oh, I know anytime I see a sine of theta, I can replace it with an x. I know anytime I see a cosine of theta, I can replace it with the square root of 1 minus x squared. And then, of course, I have my arbitrary constant. And that's an interesting idea because then I can break apart what I'm doing. I don't actually have to plug in for theta. I can plug in for the entire function and just take it away. And what you're going to find with trigonometric substitutions is that's a much, much cleaner way to solve these problems. And further, we're going to find new techniques that sort of turn these into templates that make your life easier. But I personally, just kind of editorializing here, personally I think it's better to practice mostly in this way. The reason why I say that is that those techniques, those templates actually work a lot of the times, but this gives you control over it. I personally don't remember the templates. I don't memorize them. I don't have to, because I can always construct the triangle and I can always pull out the templates. And as you'll see, what these templates do is they just give you the same thing this does. But I remember to draw a triangle. I remember how the Pythagorean Theorem works. I don't have to remember templates anymore. So, I mean, to each his own, but I think it's going to behoove you mathematically to think more in these kind of abstract ways. It's going to give you a deeper understanding.